Hey everybody, it's Eric here again, and welcome to one of my favorite parts of the course. This is the part of the course where we burn stuff. Yeah, we use combustion analysis to determine the percent composition of compounds and their empirical formula. It's really interesting how burning stuff and collecting all the products from that combustion, analyzing the products, can tell us things about what we started with in the reactants. So I'm going to go through an example here in detail, and you're going to get a sense of this. Here's the question. 14.765 grams of a compound containing only carbon, hydrogen, and oxygen is burned for combustion analysis to find its percent composition and empirical formula. So basically what we're talking about here is combustion analysis, and what I mean by that is this. We've got an unknown sample. It contains carbon, hydrogen, oxygen, and we're going to burn it. So we're going to add some exogenous oxygen. And in the end, there's only two products that are going to come out of this if we can do complete combustion, and those are carbon dioxide and water. So what we're going to do is we're going to put this in a specialized apparatus, and we're going to collect the carbon dioxide, and we're going to collect the water. And if we measure those two products, then we should be able to calculate the percent composition and the empirical formula for our unknown compound. So I'm going to walk you through a few steps here. Let's start with step number 1, which is basically doing the experiment. So let's pretend we do the experiment, and this is what pops out. So let's say we collect these two things. We collect 43.257 grams of carbon dioxide and 12.395 grams of water vapor. Now let's take these two things and work towards calculating the percent composition. Let's start first with carbon. The way to do the percent composition is first to calculate the mass of carbon inside that 43.257 grams of CO2. And this is how you do that. So what you do is you take 43.257 grams of carbon dioxide, you times it by the molar mass of carbon, which is 12.011 out of the periodic table, and you divide by the molecular weight of carbon dioxide, and that gives you 11.8057 grams of carbon in the original sample that weighed 14.765 grams. Let's do the same exercise now with hydrogen. Okay, this is how you do it with hydrogen. You take 12.395 grams of water, you times it by this quantity. I want to show you something very specific. See this 2? Okay, that's very important. This is a pitfall. A lot of people can fall into this little pitfall here. You need this 2 because if you look up here in the formula, for every 1 mole of water, there's actually 2 moles of hydrogen. So when we talk about the molecular weight of water, the contribution to that molecular weight that comes from hydrogen is 2 times 1.008. So make sure you have that 2 in there for that one. Okay, if you do that calculation correctly, then you end up with 1.3870 grams of hydrogen in the original 14.765 gram sample. Okay, so now that you have this, you can move to figuring out a percent composition, because a percent composition, really what it means is the mass of carbon divided by the mass of the sample. So let's do that right now. So there's your percent composition for carbon. It's 79.957%. Let's do the same calculation now for hydrogen. Okay, so then you'll get a percent composition for hydrogen of 9.393%. And now, if you look back up at the top of the question, it also asks for the percent composition of oxygen. How are you going to figure that out? Remember, oxygen is a complicating factor because when we do our analysis, we actually add exogenous oxygen to the equation. So we have to be really, really careful what we're doing here, that we don't know how much we added. So it's difficult to keep track of it. So there's a trick for finding out the percent composition of oxygen in this compound. Basically, you do it by subtraction. Check this out. So when you do it by subtraction right there, and you subtract the 79.957% percent composition from carbon and then the 9.393% composition from hydrogen, then what's left over is entirely due to oxygen. That's 10.65%. So that answers the first part of the question up here, which is to do the percent composition. The next thing to do is to do the empirical formula. So what I'm going to do is I'm just going to wipe this screen clean a little bit, and then I'll move to that in a moment. Okay, here's my new screen, and what we're going to be working on now is calculating the empirical formula. So I'm just going to rewrite some stuff here from the last screen just so that we're on the same page. Okay, here's our percent compositions from the last screen, and now what we're going to do is I'm going to show you the logic to think about calculating the empirical formula. Now, to simplify this, I just want you to assume for a second, just assume that we have a 100-gram imaginary sample. Okay, it's imaginary. 100-gram imaginary sample. If you had such a sample, think to yourself, how many grams of carbon would be inside it? Well, if it's 79.957% carbon, well then in that 100 grams, there would be 79.957 grams of carbon. Okay. Similarly, 9.393 grams of hydrogen and 0.65 grams oxygen. Now, when we talk about the empirical formula, we talk really about molar ratios. So what we have to do is convert these grams into moles. So let's do that right now. And you should get answers like this: 6.656 moles of carbon, 9.318 moles of hydrogen, and 0.666 moles of oxygen. And so now these are the molar ratios. So how you can write this new equation is basically like this: C 6.656, H 9.318, and O 0.666. Now you know that by convention we don't put any decimal places or we don't put any fractions inside these subscript numbers inside formulas. So one way to get rid of these fractions is to start by dividing by the smallest one. So let's divide this. Let's divide each of them by the same number. Let's divide them all by 0.666. Okay, watch why this is useful. Okay, 0.666 divided by 0.666, that's a 1. Okay, 9.318 divided by 0.666, if you put that in your calculator, get a number about 13.99. And similarly over here, you'll get a number about 9.99. Now, these numbers here just contain a little bit of rounding error, and you could probably express them with confidence like this. And we don't have to put the number 1 here because the number 1 is always implied. So there you have it, folks. That is the empirical formula for your compound, C10H14O.